Our second acid-base theory is called the Bronsted-Lowry theory. This is also referred to as the alternate theory on your region sometimes, but just so you know, the second acid-base theory we're going to be going over is called the Bronsted-Lowry theory. It's also referred to as the alternate theory on the region sometimes, but just know if it says alternate in a question, it's just referring to this Bronsted-Lowry theory, which is just the more technical term for it. So before we talked about the Arrhenius acid-base theory, where acids, when dissolved in water, release H plus or hydrogen ions, and our Arrhenius bases release hydroxide ions or OH minus ions, okay, when they are dissolved in water. So they have to be in aqueous solutions. So the Bronsted-Lowry theory kind of expands that definition of an acid. And this one deals with just protons instead. So protons is our H pluses again, our hydrogen ions. Okay, where our Bronsted-Lowry acid is a proton or H plus donor. It gives one away. And the Bronsted-Lowry base is going to be an H plus or a proton acceptor. So it's going to gain a proton. So the Bronsted-Lowry acids and bases are going to work hand in hand with one another. So both of them have to be present, okay, in order for this process to occur. Because when the acid donates its proton, it's going to donate its proton to the base that is there that will accept that proton. Okay, so for the acid example, we have our HCl. So HCl is going to donate its proton to whatever base is there to accept it, whereas that Bronsted-Lowry base, so like NH3 for example, is going to accept that H plus. Okay, so what's going to happen, we want to remember that our H plus has a charge on it. So for example, if we have a neutral HCl molecule, for example, when it donates this hydrogen away, okay, it's going to change into just a Cl minus ion, okay, because we lost an H plus, so that just leaves us with our chlorine with a negative charge. For our Bronsted-Lowry base, our ammonia in this example, ammonia is NH3. When it accepts another H plus, okay, it's going to turn into this, which is your ammonium ion. So now we have one more additional hydrogen ion on there, and you got to notice also that it has an overall positive charge. So a way for you to remember this Bronsted-Lowry theory is the alternate theory is BAD, B-A-A-D. So BA stands for bases accept H plus, and AD stands for acids donate H plus. So one thing we should go over is water, H2O, is considered amphiprotic. Okay, so amphiprotic means that depending on what water is interacting with, it can act as both an acid, so it can donate its H plus and become a hydroxide ion, or it can act as a base and accept an additional H plus. Okay, so if it accepts that additional H plus, it's going to turn into a hydronium ion. So remember, this is called a hydroxide ion, and this is called a hydronium ion. So they all sound very similar, so be very careful with that. Okay, so depending on what water is interacting with, it can go both ways. Okay, so in order for this theory to work, an acid and a base has to be present, okay? Because the acid is going to be donating its H plus away, whereas the base is going to be there to accept that already donated H plus. So an acid can only behave as a proton donor if there is a base present to accept the proton. If there is no base present to accept that proton, then the acid cannot behave as a proton donor. So we have something called a conjugate acid-base pairs, and this is basically what happens to an acid and a base after it has donated its H plus, or the base has accepted its H plus. So every acid will always have a conjugate base, and every base will always have a conjugate acid. So I like to split up our arrow to look at the left and the right side to easily see my reactants versus my products. So if we start with an acid and a base, the acid is going to donate that H plus. So every acid is going to have a conjugate base on the other side. So this would be considered a conjugate acid base pair here. So I'll just write pair. And then every base, after it has accepted an H plus, it will change into what we call the conjugate acid on the other side. So this would be another conjugate acid base pair. So you want to remember, if we're trying to figure out what the conjugate acid base pairs are, the two parts of the pair will be on each side of that arrow, if that makes sense. So the acid is on the left, its conjugate base will always be on the right. If the base is on the left, the conjugate acid will be on the right. Okay, so this is just an example of sulfuric acid reacting with water to produce a bisulfate ion and a hydronium ion. So this is already labeled for you, but the sulfuric acid H2SO4 is our Bronsted-Lowry acid. So the sulfuric acid is going to donate its H plus to water. So water in this case is going to be acting as a Bronsted-Lowry base because it is accepting that H plus. So as a result, the sulfuric acid, because it got rid of or donated its H plus, is going to turn into this bisulfate ion. So this bisulfate ion now we can call the conjugate base. Okay, so the conjugate base is what is formed after that acid has donated its H plus away. Okay, so these two, the sulfuric acid and the bisulfate ion, would be one of your conjugate acid base pairs.